Introduction to Module 6. In this video, we will learn how to use a chi-square test to test for an association between two categorical variables. Before we start, I'm going to quickly recap what we did with the chi-square goodness of fit test, which we used with one categorical variable with more than one category of interest. We stated the null hypothesis, that the observed distribution was no different than a hypothesized distribution. We looked at our observed counts in each category, and we compared the expected counts to the observed counts using a chi-square test statistic, where for each count that we had, we took the observed count minus the expected count squared, and then divided by the expected, and then for each of those categories, we added those values up to get our chi-square test statistic, and then we used a chi-square distribution to find the p-value. A chi-square test for an association between two variables is going to be an easy extension from the test statistic that we've already seen. This is often going to be called a test for independence. What it does is it tests for an association or a relationship between two categorical variables. So when we want to know if there's an association between two variables in a population, we are going to take a sample and collect some data. The data can be arranged in a two-way table because we have two categorical variables. And we want to know if they're associated. The hypotheses for a test of association, the null is always going to be that the two variables are not associated. And the alternative hypothesis, H sub A, is that there is an association between the two variables. The chi-square test statistic that we are going to calculate is going to look exactly like the one that we used for a goodness of fit test. The difference here is that we're going to have a different way of finding the expected cell counts. But similarly to the chi-square statistic we used before, we're going to need to have all the cell counts be at least 5 for us to be able to use a chi-square test. Since we've got two variables instead of just one, we're also going to need a little bit of a different way of calculating the degrees of freedom. The degrees of freedom for a test for association are the number of rows in the two-way table that we make, minus 1, times the number of columns in the two-way table, minus 1. That'll give us the degrees of freedom we'll use when we want to find the p-value for a chi-square test of association. What about the expected counts? Like all hypothesis tests, the assumption is going to be that the null hypothesis is true when we're calculating the expected cell counts. So we use the sample data to calculate them, and we're going to see that the expected cell count for each cell of the table is going to be the total for the row times the total for the column divided by the total sample size. And those are going to be the row and column totals from the two-way table that contains the data. We'll do an example in just a little bit. So the basic process for a chi-square test for association, first we make our hypotheses. Null is that the two are not associated, and the alternative is that the two variables are associated. Next, we're going to need to calculate our expected counts for each cell in the two-way table based on the observed data. We're going to have to check and make sure they're all at least 5, otherwise we shouldn't be using the test. Once we've got our expected cell counts, we'll use them with the observed data to calculate the chi-square test statistic. We'll compute the p-value as the area in the right tail above the chi-square test statistic that we calculate. And then we'll interpret the p-value and draw a conclusion. As you already know, in many coffee shops, there's a tip jar on the counter. Would you be more likely to leave a tip if the barista gave you a card with a joke to read while you were waiting? Is the joke that was used in a 2002 study that investigated the question of whether telling a joke can affect whether or not a customer leaves a tip in a coffee bar. The data were collected at a famous resort on the coast of France. Coffee ordering customers were randomly assigned to one of three groups. One group received a card telling a joke. Another group received a card containing an advertisement for a local restaurant. And a third group received no card at all. We're going to use the data that they collected from the study to decide if the study provides strong evidence that the type of card a person is given is associated with whether or not a tip is left. We're going to test a 5% level of significance. First, we're going to need our hypotheses. Our null hypothesis is that the type of card is not associated with whether or not a person tips. The alternative is that there is an association between whether a person tips and the type of card that they're given. Let's look at the data that we're collecting. Here are the data arranged in a two-way table. As you can see, the overall proportion of people who tipped is 60 out of 211. If there's no association between the type of card and tipping, we'd expect that the fraction who tip in each of the treatment groups, each type of card, to be around that same proportion. So the expected number who would tip out of the 72 people who received joke cards would be that proportion multiplied by 72, or 20.474. In general, the expected count for each cell can be found by taking the column total and multiplying it by the row total and dividing by the table total, or the total sample size. If we do this, we find the expected cell counts. I just added them to the two-way table up above, and I suggest you stop for the video for just a minute and try calculating a couple of them to make sure that you understand. The next thing we need after we calculate the expected cell count is we're going to need to calculate the contribution from each cell to the chi-square test statistic. The way that we calculate it is by taking the observed cell count minus the expected cell count squared and dividing by the expected cell count. We do this for all of the cells of the table. And when I talk about all the cells of the table, I'm talking about the ones here with the data in them. The total columns and the total rows we're not counting. So for the tip joke card cell, my observed would be 30, my expected would be 20.474. So when I subtract those, square it, and divide by the expected, I get a contribution of 4.432 to the chi-square test statistic. And I can continue to do this for every cell of the table. Again, I suggest you stop the video and do a couple just to make sure that you understand how this is being calculated. Once the contributions are all calculated, to get the chi-square test statistic, we just add them all up. Here our chi-square test statistic comes out to 9.954. Now we're going to want to use the chi-square distribution. We're going to use the right tail beyond this test statistic to find our p-value. There's our test statistic. We again need to do that to find the degrees of freedom for the chi-square distribution. And the reason I have this table here is so that we can look at it, because the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So here we have, again I'm talking about just this part of the table, so we have 2 rows and 3 columns, which gives us 2 degrees of freedom. So now in StatKey we go to the theoretical chi-square distribution. We enter our degrees of freedom, 2. Our p-value is going to be the area in the right tail beyond our test statistic. So I click on right tail. And then I change the cutoff on the bottom axis to be where my test statistic was. So my test statistic was 9.954. So my p-value now is given here It's 0.0069. Our p-value of 0.0069 is less than our 5% level of significance, so we reject the null hypothesis, which means that there is strong evidence that the type of card a customer receives is associated with whether or not a tip is left. Now, that kind of conclusion isn't particularly useful unless we know which type of card makes people more likely to tip. In order to answer that question, we can look back at the original data. If we do that, we'll see that the proportion of people who left tips is highest among those with the joke card, and is clearly lowest among those with the ad card. So, if I were a waiter working at a coffee bar, I'd want to leave a joke card with the customer. Definitely not an ad. I hope this gives you a good start with the last section that we're going to cover in the textbook, 7.2. If you find that you have questions, don't hesitate to ask.